In this video, we'll have a look at the exam of signals and systems. As you can see, this is the exam of January 2021. The duration of the exam was 2 hours for 2 exercises, one on the Laplace transform, one on the Z transform, and 2 theoretical questions. We'll go into the details of those questions later on in the video. And here were the instructions. You should probably have a look at them because these instructions will most probably be remaining the same for the next exams. Here is the first exercise. You have to solve the following differential equation. So second derivative of y plus 2 times the first derivative plus 5 times y of t is 4 times exponential of minus t times u of t. This is to make the input signal causal, and you have initial conditions on y and its derivative in 0. So y of 0 is 1 and its derivative in 0 is 2. As usual, try to do this by yourself first and push the pause button. So we'll prepare this exercise. What do we need? We need the Laplace transform of this signal over here. So either you know this Laplace transform, which is always dangerous, right? You can always think wrong and have a mistake. So the best thing is to try to find this Laplace transform of this signal over here. You remember the definition, and if you apply it to this signal over here, well, this is the integral that you have to compute. You can rewrite it as follows, and then you have to integrate this function with respect to time. This is what you obtained, and the integration bounds are 0 to infinity. This is not going to give you anything because this is going to go to 0 when t tends to infinity. So 0 here, if you evaluate this, well, the numerator will be 1, and we'll have, well, 0 minus 1 over s plus 1. So we'll have this transform over here. So this explains why when I take the Laplace transform, I have this 4 over s plus 1 over here. A mistake that is often made at the exam is that I have a minus here. This is obviously wrong because this signal between quotes is stable. It's going to 0. So when I take the Laplace transform here, I expect a pole that is to the left of the imaginary axis, and this is the case over here. I now need to take the Laplace transform of the derivative of y. This is done using this expression here. So the Laplace of the derivative is s times the Laplace transform of the original signal minus the original signal evaluated in 0. We also need the Laplace transform of the second derivative, but we can reuse this same equation, right? And the only thing that will change here is that we'll have y prime here, so the first derivative over here, and here we'll have the first derivative evaluated in 0. This is using the same expression as here, right? The signal here is the second derivative, so when you integrate this one, you have y of t. If you integrate this one, you have y prime, right? So this is kind of obvious, right? What we need here is the Laplace transform of the derivative, but we have just obtained it. So if you inject this expression in here, this is what you obtain, and if you expand, this is what you need to use, right? Do this because very often what I see at the time of the exam is that these ones are switched over here. So if we use this and we go to the Laplace domain, well, this is the Laplace transform of the second derivative, and then you need 2 times the Laplace transform of the first derivative, and then 5 times the Laplace transform of y of t, which is y of s, and then of course the Laplace transform of this signal, which we have computed before. Another mistake that is often made is that, well, this parenthesis here is forgotten. The 2 is of course acting on the y0 as well. So with this, we are now ready to continue the exercise, and if you have not completed the exercise, I suggest that you do so now and that you push the pause button. So let us continue the exercise. What we can collect here are the terms that involve a y over s, right? This is what we do over here, and the initial conditions, we bring them to the other side, and this is what we obtain. What you can then do is of course replace y of 0 by 1 and the derivative of y in 0 by 2, and this is then what you obtain. If you divide, right, this is the Laplace transform of y of t, and it's y of t that we need to obtain. So what we'll need to do is, well, partial fraction expansions, right, and then an inverse Laplace transform. If you compute the roots of this one over here, and you can simply do this by completing the squares, you will immediately see that the roots are complex conjugate. Two alternatives. The first one is to work with partial fraction that will involve, well, roots that are complex conjugate. This is probably not the way to go unless you're really liking to work with complex numbers, right? The way to go is to see that, well, you should do your partial fraction expansion like so, because this is going to lead to either a sine or a cosine that is multiplied by an exponential, right? So if you work this way, you can avoid to work with complex numbers. You have here at the denominator a third order polynomial, right? So you should have 3 constants in your partial fraction expansion, and this is the case as you can see. It is very easy to obtain a. What you have to do is take this expression, hide the s plus 1, and evaluate in s is equal to minus 1. This is going to lead to a coefficient 1, right? And then we can put everything under the same denominator again and look at the terms in s square, for instance, and s0. If you do this for s square, you'll have a plus b, and you have a 1 over here, so you see that b is equal to 0, right? And if you take the independent terms, you have an 8 here. Pay attention that you have a 5 in reality, because you have the 1 coming from here and the 4 coming from here, so you'll have 5 times a plus 1 times c is equal to 8, so this leads to c is equal to 3, right? So we can write the Laplace transform of y of t like this, but we can decompose it like this, right? So we can see here that we have here a sine, right? It will have a frequency of 2, right? And here the sigma is negative, so you'll have e to the exponential of minus t appearing. To make everything ready, what you should have here is a 2, right? We have omega 0 squared, omega 0 here, right? So we have 3 over 2. If we take the inverse Laplace transform, this is what you obtain, and do not forget this u of t here, this Heaviside function, to make the whole thing causal. Of course, you should always check results. If you evaluate this in 0, you will see that you have indeed a 1, so this is correct. But you should probably also check the derivative. So you need to compute this derivative. Here it is. And if you evaluate it, you will see that you have a 2. So this is correct as well. So here's the second exercise. You have to solve the following difference equation. So y of n plus 1 minus 2y of n is equal to n plus 1 between parentheses times u of n with an initial condition in 0 on y, and y evaluated in 0 is equal to some constant c. As usual, try to do this by yourself and stop the video. In order to solve this exercise, we'll need the z transform of a signal that has been shifted to the left by 1, right? So if this is the original signal and you take its z transform, it's one-sided z transform. So this is the z transform when you multiply this signal here by u of k to make it causal. So you only take this part over here and you apply the definition, then you obtain the following z transform. It's f of 0 times z to the power 0 plus f1 times z minus 1 plus f2 z minus 2, etc. This definition, you have to be able to find it at the time of the exam, because this is nothing else than a Laplace transform of a signal that has been sampled. If we use this same definition here on our signal that has been shifted by 1 to the left, what we'll have here is, well, this one here, but this is now f1 times z to the power 0, f2 times z to the power minus 1, f3 times z to the power minus 2, etc. And you can see that you can obtain this one over here from this one, right? All you have to do is multiply this one by z. This corresponds to shifting to the left, right? And well, if you multiply by z, it will not be entirely correct, because this one here, f0 times z, will be too much. And you see, when you shift it to the left, it disappears. So it's kind of logical that you have to subtract it, right? So the z transform of the sequence shifted to the left is z times the original z transform minus f0 times z. So again, we'll prepare the exercise. We have just obtained the z transform of the signal that has been shifted by 1 to the left, and this is zyz minus cz. This is what you see over here, and you'll have then minus 2 times y of z. We need the z transform of this signal over here, but since the z transform is linear, well, you can take the z transform of this sequence plus the z transform of this sequence. This is the z transform of a unit step, right? So here in blue, I've given the definition of the z transform, and I've shown you the formula that you can use to obtain the z transform of the same sequence but multiplied by k. In the course, theoretical course, it's shown that you can obtain it by taking f of z, taking the derivative with respect to z, and multiply by minus z. So to obtain this z transform here, we use the definition. This is what we need to compute. We remember the formula of the geometrical series, right? This is this one. This leads to 1 over 1 minus q, provided that, of course, the modulus of q is smaller than 1. This formula has been studied in the course, and I've shown you how you can kind of, well, see how you can obtain this formula using intuition, right? So if you use this formula over here to compute this z transform, you can see that the z transform of the unit step is 1 over 1 minus z minus 1. This is when you work with the variable z minus 1 But here, since we work with a shift to the left, you can see here that the variable that is natural, you can see it from the initial conditions, well, it's natural to work in z. So what we'll do here for the remaining part of the exercise is to work with the variable z. If you want to work with the variable z, what you have to do here is multiply at the numerator and denominator by z, and you obtain the following z transform. And by the way, this is the region of convergence. If you want the z transform of this sequence here, right, this is not a unit step, this is a unit ramp in the discrete domain. You take this one, you take its derivative with respect to z, and you multiply by minus z. If you do this, this is what you'll obtain with the same region of convergence, and this explains why we have here at the right this expression. First comment that we can make is that I sometimes see at the time of the exam that the variable z is mixed with the variable z minus 1. At some stage you have to make a choice. Either you work with z or with z minus 1 variable. But you cannot mix in a problem the variable z with the variable z minus 1. Here it's natural to work with the variable z, as I've said before, using the initial conditions. You can see here that in a natural way the variable z comes to the front. So what we can do now is collect all the terms that involve a y of z. This is how we obtain this expression here on the left. The initial condition is going on the other side, and what we do over here is group these two under the same denominator. Right, then we divide by z minus 2 and we have an expression of y of z. What I've seen at the exam is that, well, some students have, well, brought all this expression here to the right under the same denominator. You should not do this, because otherwise you'll end up with an expression that you'll have to decompose, right? And it will involve this c over here, right? So leave this one as is, because this is a nice z transform that you know. This is the z transform of 2 to the power n u of n times c, right? So do not bring this whole expression under the same denominator. What we'll do is obtain a partial fraction expansion of this quantity over here, and since we work with the variable z, it's, well, easier to make a partial fraction expansion of y bar of z divided by z, right? If we do this partial fraction expansion, this is what we have here, but in the end what we'll have is y bar, and we'll have a z here and a z here, and you'll have, well, z transforms that are known, right? So if you work with the z variable, it's easier to do the z transform of this expression divided by z. So this expression divided by z is over here. This is the partial fraction expansion that you should perform, right? Third order denominator, I need 3 constants. This is okay, right? So I've used the method described in the course to obtain a, b, and c, but you can choose any method you like as long as a and b and c are correct, right? So for b over here, right, I take this expression and I hide the z minus 1 square, right, and I replace z by 1. This is what it gives, minus 1. For the a over here, I have to take the same expression here, take the derivative with respect to z, and again take z is equal to 1. This will yield minus 2, right? Again, if you don't feel comfortable with this way of proceeding, you can choose another method, right? And then for c, what you have to do is take this expression, hide the z minus 2, and replace z by 2, and this leads to 2. right? So we have y of z, we have our first term, right? Here it is, and then we have this expression here, but the z has to go over here now. Okay, so we have here a is minus 2, right? This is correct. B is minus 1, and C is equal to 2. So this is a 2 over here, right? And of course, what is lacking over here is a Z, right? So we have here an expression with at the denominator Z minus 2, and we have another one over here, so we can group these two, right? And this is now our expression of y of z. And now it's easy to take the inverse z transform. So we have c plus 2 to the power n u of n, right? This is what we see over here, minus 2 times, this is the z transform of a unit step, so minus 2 times u of n, and this is, well, the z transform of our unit ramp, so minus n u of n, right? So this is the expression of the solution, and as usual we should check that we meet the condition here at the origin. We plug the value n is equal to 0 in here, we'll have c plus 2 minus 2, and this is indeed equal to c, and this feels comfortable because, well, this is correct. Well, here is the first theory question. This question should not come as a surprise, as the list of questions is on the web page of the course. So this question is: give a definition of the concept of bounded input, bounded output stability, and illustrate what is meant by a bounded signal. Then you have to give the bounded input, bounded output stability condition in the Laplace domain, given the transfer function of a causal linear system. And then you have to obtain this stability condition. So it's really proving this stability condition, starting from the region of convergence of the transfer function h of s. This theoretical question is of course covered in its detail by the theoretical course. All I want to do here is to show you what I expected as an answer. So in the first part of the question, as for the definition of bounded input, bounded output stability, and this definition establishes that for a bounded input x of t, the output of the bistable system is also bounded. So what do we mean by a signal that is bounded? Well, for that we need a finite bound m, right? And the signal is bounded if the absolute value of x of t is smaller than this bound for all t, and this means that x of t lives in the interval minus m for all t. Well, this can be illustrated as follows. If the system is bounded input, bounded output stable, then any bounded input x of t, bounded by some constant m for all t, will produce an output that is bounded as well. It is bounded here for all t by some constant L. This means that the output y of t is guaranteed to live in an interval minus LL for some constant L for all t. Well, the second part of the question asks for the stability condition in the Laplace domain given the transfer function of a causal system. As indicated over here, well, for a causal system, the stability condition asks for all poles of the transfer function to be strictly in the open left of S-plane. So all poles should be to the left of the imaginary axis. And in the third part of the question, we need to prove this starting from the region of convergence of the transfer function. So how do we prove this? Well, the first thing that you have to obtain is the region of convergence of the transfer function h of s. Remember that h of s is the Laplace transform of the impulse response of the causal system, and this region of convergence is given by this expression, right? In the theoretical course, in the video course, you will see that it is quite easy to obtain this region of convergence, starting from the definition of the Laplace transform of the impulse response of the causal system. The second thing that you need is the stability condition, but in the time domain. So a causal linear time invariant system is bounded input, bounded output stable if its impulse response is absolutely integral. This can easily be shown from the convolution integral and the definition of bounded input, bounded output stability. This is covered in the video course. So it can now easily be seen that if sigma is equal to 0 is in the region of convergence, then automatically this is satisfied and the system is bounded input, bounded output stable. And in the other direction, if the system is bounded input, bounded output stable, well, then sigma is equal to 0 must be in the region of convergence. So we arrived at the following stability condition. The causal system is stable if it can be described by a transfer function with a region of convergence that includes sigma is equal to 0, that's the imaginary axis, in the region of convergence. But this is equivalent to saying that all poles of the transfer function must be to the left of the imaginary axis. Indeed, assuming a causal system, the region of convergence of the transfer function h of s is to the right of the poles with the largest real part. This is shown in the video course. So if we want a region of convergence that includes the imaginary axis, well, the poles with the largest real part must be to the left of the imaginary axis, right? So all poles must be to the left of the imaginary axis in order to have a region of convergence that includes the imaginary axis. Here is the second theory question. In the first part of this question, you need to obtain the Fourier transform of a sample signal. And by obtain, we mean really the mathematical development. So you need to prove this expression. In the second part of the question, you need to use a drawing and of course the expression of the Fourier transform of a sample signal to obtain the Shannon-Nyquist condition for a low-pass signal of finite support. Well, the third part of the question is a more applied question. So we are given a cosine at 13 kilohertz, which is sampled at 8 kilohertz. And there is information here that says that there is aliasing. So obviously this Shannon-Nyquist condition is not satisfied. Therefore, the samples of this 13 kilohertz cosine will look like the samples of a cosine at some other frequency, and the question is which frequency, and of course you should justify your answer. The first part of the question and the second part of the question are covered by the theoretical course and the video course, so we'll not go into the details. I will just show you what I expect as an answer. For this third part of the question, I will go a little bit more in the details. So here we consider ideal impulse sampling, and the sampled function is really obtained by multiplying the original function f of t by a Dirac comb. As you can see here, this Dirac comb is a periodical function with period t of s. This means that you can compute its Fourier series. The Dirac-Combe is periodic with period Ts, so we can write its Fourier series expansion as follows. All we need to do is compute the Fourier coefficients, right? And if you go through the details, you will see that the Fourier coefficients are all equal and equal to 1 over Ts. This is further explained in the video course. We now have all ingredients to obtain the Fourier transform of a sampled signal. We know that the sampled signal is obtained from the original signal by multiplication with the Dirac-Combe. The Dirac-Combe has a Fourier series that is given over here, so we can inject that over here. We take the Fourier transform, but using the linearity of the Fourier transform, we can rewrite the Fourier transform of the sampled signal as follows, right? And using the frequency shifting property of the Fourier transform, we obtain the following expression. So we see here that the Fourier transform of the sampled signal is periodic with period omega s, right? We have here a periodic signal with a motive, well, the Fourier transform of the original signal f of t. We see that the Fourier transform of the sampled signal is a superposition of shifted analog spectra of this type multiplied by 1 over Ts. Well, let us have a look at the second part of the question about deriving the Shannon-Nyquist condition. So what you see here is the amplitude spectrum of the original signal and the amplitude spectrum of the sampled signal. Remember that the Fourier transform of the sampled signal is 1 over Ts, a sum ranging from minus infinity to infinity of f of omega minus k omega s. So we have a sum of motives f of omega shifted by k omega s and multiplied by 1 over Ts, and this is indeed what you see, right? From the expression we can see that this is a periodic function of period omega s, and really this is the motive that corresponds to k is equal to 0. This one is the one corresponding to k is equal to 1, k is equal to minus 1, and so on, right? Well, for the Shannon-Nyquist condition to be respected, we have to be able to reconstruct the signal using an ideal reconstruction filter that will select everything that is in between minus the Nyquist frequency and the Nyquist frequency. And this will be possible as long as, well, these shifted motives do not overlap. And in order for the motives not to overlap, well, you have to have this frequency here, omega s minus omega max, to be larger than omega max, right? So omega s minus omega max is larger or equal to omega max. So this leads to the Shannon-Nyquist condition that the sampling frequency is larger than 2 times the largest frequency contained in the signal, and this is sometimes written in terms of the Nyquist frequency that should be larger than omega max. So this is the answer for the second part of the question. So let us now have a look at the third part of the question. Well, the spectrum of the original cosine at 13 kilohertz is given over here. This should not come as a surprise because this cosine will assume that it has amplitude A, can be seen as a phasor turning counterclockwise of amplitude A over 2, right? And this will yield here a spike, an impulse at 13 kilohertz in the amplitude spectrum, and there will also be another phasor turning clockwise, right, of the same amplitude, and this will yield here this impulse at minus 13 kilohertz. Let us now concentrate on the amplitude spectrum of the sampled signal, and we have just obtained an expression that is this one over here. So this can be seen as a sum of shifted versions of the motive. The motive really is the Fourier transform of the original signal, and well, this sum of shifted versions has to be multiplied by 1 over Ts, and in this sum you have an infinite number of terms, and I have shown the terms that correspond to k is equal to minus 2, k is equal to minus 1, k is equal to 0, k is equal to 1, and k is equal to 2. So what we'll do now is construct this amplitude spectrum of the sampled signal. Before we continue, I have shown here the reconstruction filter. This is a filter, this is this ideal reconstruction filter of amplitude Ts in between minus 4 kilohertz and 4 kilohertz. Remember that 4 kilohertz is the Nyquist frequency, it's the sampling frequency divided by 2. And below minus the Nyquist frequency, this is 0 here, and to the right of the Nyquist frequency, this is 0 as well. So the reconstructed signal will look like a cosine of at most 4 kilohertz, right? So after sampling, our 13 kilohertz cosine, because of aliasing, will look like a cosine of a frequency that is at most the Nyquist frequency, right? So an answer like the one that I've seen in the exam of 52 kilohertz is really not possible, because the answer must be at most, well, the sampling frequency divided by 2, which is the Nyquist frequency of 4 kilohertz. So what we have done here is to show, well, the contribution of the motive that corresponds to k is equal to 0 in the amplitude spectrum of the sampled signal, right? So we have here a contribution at 13 kilohertz and minus 13 kilohertz, and here the amplitude that was a over 2 has been divided by Ts. And clearly after reconstruction, right, well, our cosine will not look like a cosine at 13 kilohertz, right, because the maximum frequency that can be selected is 4 kilohertz, and this is kind of normal since the Shannon-Nyquist condition is not satisfied. In order to see a 13 kilohertz cosine at the right frequency of 13 kilohertz, we need to have a Nyquist frequency that is at least 13 kilohertz, which is not the case in this example. Well, in my infinite sum, I have now shown the contributions that correspond to k is equal to minus 1. This is in orange, and to k is equal to 1 in brown. So what you have to do is take the original motive minus 13, 13, right? And in yellow here, we'll subtract the sampling frequency of 8 kilohertz. So minus 13 minus 8 minus 21, 13 minus 8, 5, right? And for this shifted motive, k is equal to 1, we take the central motive and we add the sampling frequency. So minus 13 plus 8, this is minus 5, yeah, and 13 plus 8, this is 21. So we have still not found under what frequency our sampled cosine will appear, because we have to select a frequency that is smaller or equal to the Nyquist frequency. Well, in my amplitude spectrum here, I have now added the terms in this infinite sum that corresponds to k is equal to -2, right? This is the motive shifted by 2 times the sampling frequency to the left, and k is equal to 2. This is the central motive shifted by 2 times the sampling frequency to the right. Okay, indeed, you see that -13 minus 2 times 8, this is -29, 13 minus 2 times 8 kilohertz, -3 kilohertz, and if I do the same but in the other direction, we'll have -13 plus 16, this is 3, and 13 plus 16, this is 29 kilohertz. So of course I should keep on adding terms over here, right? But there will be no other k that will give a contribution in the frequency band -4 kilohertz, 4 kilohertz, which corresponds to the band minus the Nyquist frequency, the Nyquist frequency. And we can now see that a cosine at 13 kilohertz sampled at 8 kilohertz will look like a cosine at 3 kilohertz. So this is the correct answer with the correct justification. To help you with this, I have created 2 M files, and these M files are available on the web page of the course. The first one explains what happens for this particular example of the exam in the time domain. So we have here our cosine at a frequency of 13 hertz here. I have replaced kilohertz by hertz, and this cosine is sampled at 8 kilohertz, right? So this is the code to plot the original cosine. This will plot the cosine at the sampling instance. You can see here that t is equal to n times ts, the sampling period, and we will plot here the alias signal, right? So this cosine at 13 hertz, because the sampling frequency does not meet the Nyquist condition, will appear as a cosine at the aliasing frequency of 3 hertz. Let us now run the code. This is the cosine at the original frequency of 13 hertz. Here you will see the cosine sampled at, well, the sampling period 1/8, right? And, well, the original cosine, because the Nyquist condition is not met, will appear as a cosine at the aliasing frequency of 3 hertz. Well, the next file will allow you to see things in the frequency domain. This file will actually plot the amplitude spectrum of the sampled signal. It is assumed here that the sampled signal is a cosine at a given frequency, here 13 kilohertz, and that it is sampled at a given sampling frequency, here 8 kilohertz. But in this file, of course, you can change the frequency of the cosine and change the sampling frequency as well. In the first part of the code, the reconstruction filter is plotted. Next, the spectrum of the sampled cosine is shown. Remember that this Fourier transform of the sampled signal is composed of an infinite sum ranging from -infinity to infinity, and in this infinite sum, this file will show the terms corresponding to k is equal to 0, 1, -1, 2, -2, 3, -3, and these shifted motives will be shown in the following colors, as you can see. Well, let us run the code. So this is the reconstruction filter that will select frequencies that are in between minus the Nyquist frequency and the Nyquist frequency, so minus 4 kilohertz and 4 kilohertz. So this is the motive that corresponds to k is equal to 0. This is the one that corresponds to k is equal to 1, k is equal to minus 1, k is equal to 2, k is equal to minus 2, k is equal to 3, and k is equal to minus 3. So you can see that, as observed before, our cosine sampled at 13 kilohertz will appear as a cosine at 3 kilohertz because the Nyquist condition is not met. To see if you have understood this fully, try to do the exercise by yourself with 13 replaced by 18, 8 replaced by 10 over here, right? So here it's also 18, and the question is, well, when this 18 kilohertz cosine is sampled at 10 kilohertz, under what frequency will it appear? Well, to see this, I have changed the values in the file, so I have now a 18 kilohertz cosine sampled at 10 kilohertz. So we can now run the code. So this is the reconstruction filter, right? And this is the central motive corresponding to k is equal to 1, minus 1, 2, minus 2, 3, and minus 3. And you can see that the frequency that is selected by our reconstruction filter is 2 kilohertz. So our 18 kilohertz cosine sampled at 10 kilohertz will appear at a frequency of 2 kilohertz.